Well, let's work a simple example problem along the lines of what we've been discussing. It actually it's a very simple problem, and it sounds a lot worse than it actually is. So here we've got 2 moles of a monatomic ideal gas at 10 bar pressure and 300 Kelvin is expanded from one to the other. So it's an isolated system, and while remaining isolated, it's so no heat in or out is expanded into a vacuum from V1, which is 1 liter, to 20 liters, V2, so initial and final. And you're asked to find delta S and delta Q reversible for the process and use the Shukura-Tetroda equation. So since they said use the Shukura-Tetroda equation, well, I wrote it down. Here I've got T in this equation is 300 Kelvin, and N, the number of particles, is 2 moles, so 2 times Avogadro's number. And I need to calculate delta S, which is S2 minus S1, and I use this for S. So the final is the final volume V2, everything else is above. And the initial I have to subtract off N KB times this expression, where the only thing that's different is the volume is V1. I can factor out the NKB out front, and then I've got the difference of 2 logarithms, which is just the logarithm of the ratio. So this term on top in the numerator, and this term on bottom in the denominator. And as you see, you get lots of cancellation because the masses are the same in this case. I'm left inside, the logarithm is just V2 over V1. And then we arrive at this equation, which you probably could have, if you'd remembered it for an isothermal process in an ideal gas, then is just N KB times the natural log V2 over V1, and this, of course, is the number of moles times the ideal gas constant. So you could have jumped here if they hadn't said we use use statistical mechanics concepts, the secure Tetroda equation. And in our case, N is 2 moles, R is 8.31, and then V2 is 20, and V1 is 1 liter. The liters go out, and we get this expression: 2 moles, 8.31 joule per Kelvin mole. Moles cancel. And when I multiplied that out, I got 49.8 joules per Kelvin. And since there's roughly 4.2 calories, 4.2 joules per calorie, then I can divide this by 4.2 and get the number of calories per Kelvin if you want. But either one of these is acceptable. For a reversible process, delta S is just delta Q reversible over T, and so I solve that for delta Q reversible. And all this is occurring at the temperature 300. And delta S, well, I come up and pick really either one of these up here. And when I multiplied 300 times this, I got 14.9, and 300 times this one, I got 3.57 kilocalories or kilojoules, respectively. Remember, the difference between these reversible and irreversible is that if I suddenly pull this piston out on this gas to here, so that V2 was 20 and V1 was 1, then I basically get a free expansion, and that becomes irreversible. If I do it quasi-statically and gradually pull this out, coming to equilibrium at all stages, then I get a reversible process. So just a little quick review of reversible and irreversible on these kinds of systems. But pretty simple problem.